Good evening. I've got a little presentation for you guys called A Bump in the Night. It's going to be a fictitious outage, and we'll go through the steps needed to make it a successful forced outage. So a little intro to Sulzer. We're a Swiss-based company, been around since 1834. Our location in LaPorte is 50 years old, 48 years old, somewhere around there. We employ 500 full-time employees at our location in LaPorte, focused on all rotating equipment. Jim Newrohr and I will be going through the presentation today. Mr. Newrohr has been in the gas turbine industry for 12 years and primarily focused on F-class and heavy industrial turbines. Myself, I've been in the gas turbine industry for 15 years, focusing on heavy industrial and aero derivatives.
Thank you, Michael, for that. We'll start right into this fictitious event with the bump in the night. During nighttime operation of a combined cycle plant running 7EA DLN1 machine, customer is running at full speed, full load, and receives a notification in the control room of an emergency trip, which has taken unit number 1 offline. As the turbine comes down, it's all hands on deck to determine what occurred during this nighttime operation. While assessing the unit, operators will go to the turbine deck to look around for any readily accessible damage that can be found. And for the purposes of this presentation, the site does have bypass ability, so the single unit offline and unavailable does not take the entire plant or power block offline. But now it's all hands on deck to determine what our next steps are, what the impact to operations is going to be, and how we get this unit back online. So our first step in all of this, once we've made sure that everyone's safe and accounted for, is to take a step back and take a breath. Rising stress levels are not going to bring this situation to a close any sooner. The worst has already happened. Now we need to get into assessing the condition of the unit. And our first steps for that, since there was no readily available damage that we could see from the turbine deck, is going to be opening up the unit's borehole or bore scope hole points and getting in with a bore scope. While bore scoping the unit, it's noted that there is heavy compressor damage seen around the 5th stage with collateral damage to the aft stages of the compressor. At this time, management is making a decision to contract a field service company to perform a more thorough tops-off inspection. We discussed the steps forward from this point of plant and asset management reaching out to a field service company, but obviously there are several steps that occur between the event and this point. There will be initial meetings and calls after the unit comes down to distribute information to the applicable teams, plant management and asset management in most cases. In the case of a utility, dispatchers will need to be informed that the unit is out of commission. ISOs in the states or other off-takers or power purchasers will need to know and be informed of the outage. Insurance companies will need to be brought up to speed and kept to date on current findings. We aren't skipping these items, and we know that they won't be skipped over in the course of the project, but this time is the divergent phase of the project. Will the plant have multiple points of contact as more and more companies get involved with findings, or will there be a single point of contact at one company handling all of these items? All of this is determined at this point. So that's where we're going to take it and start moving forward. And we'll start that after the decision has been made to move forward with the field service company with the mobilization of the field services crews. These crews arrive on site, and as previously discussed, we know that there's going to be heavy compressor damage on this unit. So with the field service crews, rotor stands will also be arriving on site at the same time. Initial meetings over what has happened up to that point will take place. JHAs and lift plans will be discussed and approved between site personnel and project management and site supervision of outage services or field services crews. The doghouse will be removed to access the turbine deck. Crews remove horizontal joint bolts to allow crane to remove top half cases, and visual confirmation of a compressor wreck is observed, stage 5, with collateral damage to aft compressor. So the confirmation of the initial findings here is important, and documentation of those initial findings is imperative. The Rcfa report is already opened at this point, but this is the first major item that will be addressed. At this point, preservation is key. The first objective of this outage and any outage is going to be safety, but the second objective of this particular outage, being that it was forced, is an Rcfa. At the moment that the compressor wreck is observed, preservation mode must be in place. FME covers are in place. We'll be protecting all potential crack or initiation sites and any other damaged surfaces on both the affected stators and rotating assemblies. The lift plan will be reviewed, and we'll start removing the rotors from the cases at this point and set the rotors off to the side on rotor stands. And with rotor out of the way, these Rcfa procedures can begin. The work provided here will decide the outcome of the Rcfa in the long run. Maintaining crack surfaces can maintain chemical property makeups found on propagation sites. Ensuring a good plan is in place with the outage service team, supervisors on site, the site crew, engineering staff, and project manager. And then we need to ensure that these plans are being adhered to throughout the project. This is where we're going to be able to determine the cause of this outage. And this is going to be absolutely imperative moving forward. Once the unit is opened, the condition is assessed, the procedures are in place, and we've started with preservation of the unit, we're going to move into the next steps. On-site activities and off-site activities will both begin at this point. We'll be loading up the unit rotor and all components as they come out of the hot gas path and combustion sections onto trucks to be moved to off-site activities. And during that same time, on-site activities will move forward as well. So data gathering from the unit and operation and identifying highest probability factors or failure indications will begin on-site. The field service crew will start a major inspection, including pulling the remaining hot gas path and CI components. Those components will then be sent to a shop, as I discussed, with the rotor, and compressor case cleanup can start taking place as identification activities wrap up. This will also include going through to make sure that there is no foreign material throughout the air cooling systems within this gas turbine. Off-site activities, the rotors will arrive at a site, the components arrive at a site for shop evaluations. Engineering will give an initial assessment of the condition of the rotors and the components, and then engineering will work with the field crews and project management to identify material for the Rcfa. The Rcfa is started in a materials lab with material replicas, fracture surface review, and other items. Now that this is starting to split, now that the project is splitting into on-site and off-site activities, there are many balls in the air here and many moving factors that will change on a day-to-day basis. Project management starts becoming complicated now. As we discussed earlier, one of the first big calls of the management team that they're going to have to make is based on selecting vendors for support. A one-stop shop with a single point of contact, multiple vendors, or the help of an owner's engineer will all have to be decided upon. The outage itself may not have been planned, but the thought that goes into these early decisions could make life more or less difficult as the project moves forward. We and many others out there in the industry have seen these projects go on with people who have planned for all scenarios and people who have hoped that it won't occur. And what we've seen across the board is having an emergency plan thought out at a basic level at the very least, and knowing vendors who can support, and having that in place can make life easier. And we would suggest that for anyone listening.
So we'll move into the offsite activities. The first step is rotors and components arrive at a repair facility. Definitely apologize for that. So anyhow, let's get back to off-site activities. So prior to the rotor arriving to the facility, field service TDs and their project managers will have alerted the shop as to the type of damage to expect. As soon as the rotor is offloaded and safely onto stands, engineering should ensure that the fracture surfaces are still protected. At that point, then they'll release the rotor to operations to start the as-received rotor inspections. So these, in this picture, it shows a coupled 70A, which happens every once in a while, but at this point, we're going to do a thorough visual inspection. We're going to go ahead, set it up in V blocks or in a balance machine and go through runouts, check balance. After the check balance is approved, we'll go to grit blast and NDE. While the rotor is going through the as received inspections, engineering is going to continue out the Rcfa process. The fracture surfaces are going to be examined, and it is noted with the failure occurring at stage 5, the compressor rotor will need an unstack. So going through the next several slides, we're going to have compressor and turbine sections split up. Compressor is always going to be on the left-hand side of the slide, turbine on the right. So during the detailed rotor inspections, compressor blade damage was noted, which warrants a compressor rotor unstack. During unstacking of the compressor rotor, we noticed galling of 7 rabbit pits that will need to be addressed during the repair phase. We also noticed internal web corrosion that will need to be addressed with an appropriate coating. For the turbine section, the as received balance and runouts looked within allowable limits. However, while doing rock lift spread measurements, the technicians noticed that the readings were outside of allowable limits. And this could be corrected with coatings as well, which we'll discuss a little bit further. Also, while inspecting the turbine section, bore scope inspections down into the coolant slots exhibited similar corrosion attack as the compressor side. So as we can see in the photos above, compressor blades were identified during the visual inspection to show FOD and tagged. Compressor rotor unstack process is going to start by unstretching the compressor through bolts. When all the through bolts are unstretched, the bolting can then be removed and we can start the unstacking process for the compressor discs. Similarly, on the right-hand side, on the turbine section, turbine bolts will need to be unstretched, then the turbine section can be unstacked. We'll then perform further visual inspections, NDE inspections, dimensional and runout inspections on the disc, as well as inspections on the fasteners, and make recommendation for reuse. So the pictures on the slide Those are 70A discs, compressor discs on the left-hand side, coming apart in a stack pit. The picture on the right-hand side is the turbine section. It has first stage and second stage turbine buckets removed at this point. Third stage buckets are still in, and you can see a couple, two of the bolting, turbine bolting have been removed, and we're working on progressively removing the rest. So the first step after all the as received inspections have been completed, findings are to be addressed with the client. A path forward for the repair processes is agreed upon. At this time, engineering has performed material replicas of multiple fracture surfaces, has analyzed the operational history that was given to us by the client, and has preliminary results for the Rcfa.
So this is where keeping an open channel of communication is key with this large of a project and so many fluid items. A single point of contact in a project manager is an occasionally underutilized position. Whether this project manager is a single point of contact within the single company for all scopes of work, or this is an external owner's engineer supporting the site to keep multiple companies' updates in order. This is a critical position from a high level and can work as a sounding board for discussions and results or paths forward with site personnel. Again, highly recommended.
So at this point, the client and the repair facility has agreed upon path forward to overhaul the rotors. For the compressor rotor, as seen in the left-hand picture, rabbit foot repairs have occurred. Bearing journal grind activities have been completed. Replacement blades were manufactured and installed. Individual bladed discs have had a anti-corrosion coating applied, and forward and aft coupling faces have had runout corrections completed. In the right-hand picture, the turbine section being assembled in the stack pit, the turbine discs have had a nickel aluminum twin arc coating applied, and this was to eliminate the rock lift spread issues. And then each individual disc and spacer has had the anti-corrosion coating applied. So getting in a little on the anti-corrosion coating. So Sulzer's got a nomenclature. It's a A for air spray, but this coating is a anti-corrosion coating that can be applied to the turbine or compressor side. It's an aluminum chromate phosphate coating, which works as a cathodic protection against the base material. So simply put, the base coat acts as an aluminum reservoir for the cathodic protection. The base coat is the active coating, and the blue coating that you see in several of these pictures, that is an inorganic sealer top coat. So similarly, compressor discs on the left-hand side. These discs had the web areas coated with the anti-corrosion coating. However, they did not have the blades coated. For this picture purpose, these are Carpenter 450 blades. On the right-hand side, there is a bucket, first stage turbine bucket being slid into a rock lift spread corrected turbine disc, and they're doing rock lift checks to ensure that the coating applied meets the criteria needed. Do you want to answer a question real quick that just came up?
Yeah, go ahead.
So Stephen asked a question: have the coatings been analyzed for water wash deposits to avoid additional material disposal costs? Stephen, can I take that question offline for you? That could be a lengthy explanation. You got it. Appreciate it.
So we're going to take a pause here and talk about how important it can be keeping components on hand that can be considered consumables and how imperative it is to these rotor projects. With metal market fluctuations that we're all currently seeing and possibility for long lead times, a shop having the foresight to keep these items in inventory can keep projects on track when abnormal findings occur. For example of how this could look, Sulzer tends to keep many common bolting inserts and other requirements for multiple units and multiple makes and manufacturers, GE, Siemens, Westinghouse, Legacy, or F-Tech in-house. Having on-site manufacturing capabilities can also give the vendor the power to and the power operator a leg up in the case of an unplanned outage. Whether or not the replacement blades for your specific make and model of turbine are on the shelf, a plan can quickly be implemented to start machining compressor blades and keep the ball moving forward. In this example, compressor blades were not available, readily available either in the marketplace or in-house. So Sulzer was able to move forward and start manufacturing the replacement blades for the compressor section of the rotor to keep the project moving and get this project wrapped up quicker.
Thank you, Jim. So now we're going to start bringing off-site activities back together. After the recommended repairs and coatings have been completed, we'll now start the rotor stack process. Prior to the stacking, Sulzer performs individual disc balancing. This is done on a tabletop single plane balance machine. This operation helps eliminate excess balance weights during the unit rotor balance. Compressor disc mating faces will be honed prior to the stack. And in this case, we reuse the compressor through bolts because they pass dimensional and NDT criteria. So in the left-hand picture, we can see a completely coated compressor going back together. The web areas and the blading have had the anti-corrosion coating applied. And in the right-hand picture, the turbine stub is being prepped to set in the stack pit to start stacking discs and spacers. So once the rotors have been stacked, Sulzer will start the stretch process on the compressor and turbine rotors. We utilize a progressive stretching process for these rotors. Once stretch is complete, the rotors will be removed from the stack pit. So in the compressor side left-hand picture, you can see some stretch tooling. It's got a lift and mandrel on top, and the right-hand side, the turbine section's down in the stack pit, and it looks like they're flying in the third stage turbine disc with a fixture. So now that we've stacked and stretched the turbine and compressor rotors, it's time to check runouts and balance. A runout result that is not within specifications could indicate an improper stack or stretch. So this is an important time going through the rotor process. Also, since we performed individual disc balancing, minimal balance corrections will need to be made.
And for all of those involved, if you're not currently aware, Sulzer does have individual pages on LinkedIn and YouTube. And over the coming weeks and months, we'll be uploading videos of these stacking activities and balancings for our viewing audiences to keep up to date and see these projects in process. So stay tuned.
So before we move to the next slide, Nick had a question. How long did the machining of the new compressor blading take, and did it impact outage critical path? Since it's a fictitious outage, yes, it did not impact the outage time. One quick note is Sulzer does keep a tremendous amount of stock or blade material on hand. So we can typically turn compressor blades well within the envelope of having the turbine rotor go through the repair process.
And in our manufacturing facility here on site, we have, is it 15 different CNC machines, multi-axis CNC machines that we can make available for these types of expedited works to make sure that we can continue that process moving forward and get these blades manufactured on short order.
And then one further question: how long did the new rotor expected to be in operation draw all the new replacement parts? So we would, as a third party, we would recommend the customer to utilize the OEM recommendation for runtime and run cycles. So get back to GER 3620, but it'll be a major run cycle. And Mr. Dunn, yes, sir. We're talking about the shop in LaPorte, which is right east of Houston. So now that the rotors have been completed, successfully completed, customer witness went well, we're going to move on to the Rcfa side and the material evaluation. So those involved in RCFAs know it is somewhat time consuming, somewhat analyses heavy. So we wanted to just throw up some macro or some micrographs of what could be observed during a typical RCFA. In the right hand pictures, you can see some fracture initiation sites. You can see some striations, some beach marks, and then in the left hand picture, you can actually see a crack or a linear indication in base material. So while the RCFA is going on, not only are they looking at material replicas or analyzing the operational run data, but they're doing chemical analyses to see if there's any intergranular deposits or if there was any external contributing factors to that failure mode. And then the materials engineers and the engineering group need to take those that data that they've found and collected and then review it against published base material properties of whatever that base material is on the failed part.
And just like we stated earlier with how important this this preservation mode is on site, this is the result of that. If we can keep that preservation in mind and key early in the outage, it can support the RCFA through these material evaluations and make everyone's life just that little bit more easy when it comes to these very complicated systems and analyses.
So Benjamin has a question. Do you high speed balance the rotors or just low speed? So Sulzer's typical recommendation is for a GE heavy frame turbine to not at speed the rotor or not high speed the rotor. It's a rigid rotor. It's not a flexible rotor like a Siemens Westinghouse. So at this time in this fictitious forced outage, we just performed a low speed balance. And thank you all for the continued questions. So moving on, this is for people on the call that have never been inside a metallurgical lab. These are just a couple pieces of critical equipment that should be in any component or gas turbine repair facility. In the upper left-hand picture, you'll see 4 stress rupture machines. These machines are used to put load under temperature onto a test specimen. If you look at the picture below it, it's a cut up bucket. So that bucket has been deemed scrap by the shop and then agreed upon with the client. This bucket has been destructively tested to determine the remaining life for the remaining customer set. So these machines will prove that the buckets or the other parts that you want to have a life assessment actually either do or do not have remaining life. And then the right-hand picture, you can see I hope Wayne Greaves is on because now you're famous, but you can see Wayne Greaves sitting at a scanning electron microscope. Wayne is our senior metallurgist and he's been with Sulzer for, I believe, 33 years. But the scanning electron microscope allows us to look at finer detail of base material, of cracks, of coating compositions, intergranular, just a really nice piece of machinery that most labs do have and should have.
E sulle terra lece. Yeah. We
So we've discussed the on-site activities. We've discussed the rotor inspection overhauls. We've also hit on the RCFAs and some coatings. So let's not forget we had the component or the hot gas path and combustion parts that were pulled out of the forced outage unit and sent to the shop. So we'd like to go through the inspection and repair overview of what you could see at any component repair facility. So these parts will show up into a ship and receiving department, and their photographs will be taken. They're going to record all serial numbers and part numbers. Those parts then get shipped to the specific department, whether it's combustion, blades, or nozzle departments. And at that point, that department's going to perform incoming and visual inspections of the as-run components. They'll then put the parts up in fixtures, whether it's a 360, slide through, etc., and take dimensional data. After engineering approves of the income and visual and dimensional, the parts will then go to a grit blast to remove any coatings, thermal barrier coatings, M-crawlies, or oxidation or just general turbine nastiness. Once the very conservative grit blast occurs, those parts will then go to an NDT. We'll talk a little bit more on a couple slides later about certain NDT operations. And at that point, the inspection of that component or set of components is complete. Engineering or tech reps are going to generate a incoming disposition, which will encompass all inspection findings, and then they're going to generate a recommended repair. Once that recommended repair and proposal is discussed with the client, those parts being, most gas turbine parts are nickel and cobalt superalloys, so most all gas turbine components need to go through heat treatments. They'll go through a solution anneal, weld prep. Those components will then be weld repaired, in-process NDT inspections, in-process dimensional inspections, and then once the in-process DIMS and NDT is completed, they'll go through a post-weld heat treat followed up with a NDT, post-weld NDT. Once the components are crack-free and engineering approves of them moving forward, final dimensional data is taken, final visual, final coating thicknesses, and generally it's held for a customer witness point. Upon approval from the customer witness, we'll box, prep, and ship the components per the purchase order.
So the pre-weld heat treatment or solution anneal that Michael discussed as being the first item of the repair process helps give everyone a full picture of the repairs needed. As he discussed, this can relieve stresses and further open cracks that are necessary for blending operations and then welding operations to take place. So the placement of this step represents an industry-specific typical process that is seen across the board in terms of RFQs received from our customers. Sulzer has started to push its customers to considering this as a part of the inspection process, as we feel it can give a better idea of the full restoration needed for a component moving through the repair process with less surprises later on throughout the project. This is something that does not change the overall cost of the repair process. It just shifts where costs are throughout the process. Sulzer would love to expand that conversation with anyone interested. Please feel free to reach out for any details.
Thank you, Jim. So before we move to the next slide, Mr. Tim has a question, which is a very difficult question to answer. So when the Rcfa is inconclusive, how do you proceed? Generally, a failure of similar modes has happened. They're usually followed up by the OEMs reaching out with TILs, technical information letters, or you can reach out to your certain user group depending on the gas turbines that you run, and you should be able to find some sort of failure mode or mechanism that mimics yours. But if you don't, unfortunately, that has to be a business decision made how to move forward or how to proceed. You know, and it can be made with a service provider and as a group discussion.
And to break that down a little bit further, the Rcfa is just that. It's a root cause failure analysis. We, or anyone who's in charge of these Rcfas, while they can provide a lot of clarity, what we're really doing is giving you a picture of the findings. And that report, those findings, sometimes can lead to a very clear picture, and sometimes it can be, as you described, a bit inconclusive. But what the goal is to further understand what happened, where we think it may have happened, can be conclusive or not conclusive. But putting together that story and what occurred because of something, or trying to figure out what the propagation sites were, and what the ensuing failures were after that, is just as important to plan for those items in the future. So we'll give you a picture of what the findings were, and then, you know, it's going to be up to everybody involved to try to decide a path forward.
Thank you for the tough question, Tim.
So moving into a bit of a further breakdown of a component inspection and what goes into it. There's going to be multiple factors throughout this process, starting with after mechanical grit and everything has been opened up, those NDE inspections. So visual, FPI, red dye penetrant, ultrasound, immersion ultrasound, eddy current tests will all be performed on these components as they move through this phase. We're also going to be looking at a lot of components through a digital X-ray. The one that Sulzer has here in site is a multi-axis, so it's a 5-axis digital X-ray where we can take views from different planes throughout the component to get a better picture of what's happening. If we can see a shadow in one, then we can look into it further with that 5-axis machine. And then along with that, dimensional inspections will take place, whether it's the 360 fixtures for nozzles, the meatball, as Michael had described it, where we set up TPs in a fixture that mimics first stage nozzle or first stage vane touch points, as well as touch points with side seals, partition slide throughs for fixture checks on both nozzles and shroud blocks, and disc simulations for buckets and blades. All of these will be making sure that the components still fit next to each other and form a concentric circle when going back into the unit. And also make sure that the blades and buckets, if they're shrouded, have not experienced any tilt or twist relative to the buckets next to them, that would cause an inability for them to be repaired or an inability for them to be reinstalled when they get back onto site. So there are fewer surprises getting back into the installation of those components. Michael had talked about a mechanical grit blast that is done on site. That is a conservative process where we remove the TBC and then get down into the M-Crawley coatings on these components. And then a heat tint takes place. And during that heat tint process, we'll see if there is any residual coating that is left over, at which point that residual coating would be blended away, hand blended away. CMM inspections are also integral to these components, especially shroud blocks to make sure that tip height clearances are met, and buckets and blades, especially those that are shrouded, again, to make sure that there are no tilt or twist being observed in those components that would make it more difficult for those components to go back into the unit upon completion. Flow testing is provided within our and many other facilities, whether it's gas, usually air, liquid, combustion, and internally cooled hot gas path components all receive this. And this is especially the case during an unplanned event where there could be debris that has made its way into cooling passages within the unit. Those passages being blocked could cause debris to flow into these air-cooled components in the hot gas path section, where we would want to make sure that all passages are cleared so we don't have gas turbine components that are receiving a lack of airflow and then shortening their life expectancy because of that. And then engineering, again, will provide a full disposition and final review with the customer. The big importance that we see here, especially in these unplanned events, is having in-house items in any vendor facility where these parts are going to be going to be inspected and then repaired, especially in a project of this magnitude. Otherwise, if sub-vendors are being brought in on multiple facets of this inspection process and then the ensuing repairs, we start to build more and more channels of communication and reporting and information. Information could be missed, delays could occur, slowdowns from trucking or movement of the parts could happen, and with any of these additional touch points, if things can come up, there's a likelihood that they will. So making sure that whoever you're working with has in-house capabilities for all items can be imperative in these times.
Now that, excuse me, now that the inspection, some of the processes have been described and talked about by Jim over the past couple of years, just changing the condition of the components when they come out of the turbine. So weld repair and blending of fretting, we'll do what needs to happen is flow test deviation correction. So any of your flow testing of your internally cooled buckets or nozzles, your combustion components, I can guarantee you they're not going to be close. So a deviation correction will need to occur. Any dimensional restorations for buckets in the bottom picture, induction welding can be electrical discharge machining. Machines help speed the repair process. So cooling holes that you can see up on that first stage nozzle segment can be welded up completely and then reestablish the holes with the EDM, and then CMM dimensional inspections, which ties into Mr. Vogel's question. Is Sulzer using any white light scanning and deviation overlay comparison to new parts as part of the Rcfa process? CT scan, FEA modeling to help analyze failure modes. So, Richard, yes, Sulzer does use white light overlay scanning. Sometimes we do not have scans of new OEM manufactured parts, but as we get them in the shop, we will put them in our catalog. We do quite a bit of overlays, whether it's in process white light overlays, in process ferro arm overlays. But yes, white light can help in the Rcfa identification process. For CT and FEA modeling, we can take that offline. It could go either way. Jaime, Mike, we've lost your audio. Can everybody hear us? Thumbs up.
Is there anything we need to go back over that was missed?
No, I think we're fine.
Okay.
Good deal. It's been a technically challenging presentation between alarms and audio. So now we're through the component repairs. Thank you for all the thumbs up. Some of the enhancements and coding improvements throughout the time, Sulzer's tried to stay with the times as the turbine run profiles have changed. Everybody wants to skip combustion inspections now. They want to run hot gas path to major, and we get it, right? That's a business model that makes sense. Less money, more revenue. So there are definitely some coding improvements that can be applied, whether it's chrome carbides, whether it's twin arc spray M crawlies. The twin arc M crawly is generally applied to the outside of some combustion components, transition pieces, combustion liners, in certain models. Another way to extend intervals on combustion components to where you can run hot gas path to majors is material upgrades. So whether it's a base material change to a better corrosion resistant material, or it's a thickness change to minimize any distortion of your combustion components, we have those in-house. For the hot gas path, we have strain tolerant TBCs, which is an extreme temperature resistant thermal barrier coating. It was devised for F-class machines, but now that we're seeing the cycling activities of quite a bit other turbines, these strain tolerant coatings can be applied on BE class components as well. And everybody wants to get the most output from your gas turbine. So really, if you take a close look at your clearance sheets, income and outgoing clearances, we've got some coating systems that can be applied to tighten up those clearance between buckets and shrouds to allow you to try to get the most output from your turbines. We also have combustion system optimization. Mr. Richard Vogel asked a question here 10 minutes ago, but Richard was paramount in when he worked for Sulzer at implementing this combustion system optimization. And basically, we're looking at air fuel ratios for not only the fuel nozzles, but the individual fuel nozzle tips, the fuel nozzle bodies, the combustion liner, and in some instances, the transition pieces. So when we balance out the combustion system, you're going to get a reduced tune time. You're going to drastically decrease your temperature spreads, and you can minimize your scrap rate for the components that we're going through the optimization. So a couple questions before we move on. Mr. Scott, I believe CCJ will be pushing the presentation out to all the attendees. And then David, will the anti-fouling coating be used in Sulzer? We have an anti-fouling air spray coating that we generally do not use on a gas turbine. And it's because the material that allows for the anti-fouling to occur will actually deteriorate with the operational temperatures in a turbine. The anti-corrosion coating, however, does in a gas turbine operation does help with fouling to a degree. So all offsite operations have been completed. Your rotors overhauled, your components have been repaired, and it's time to send them back home and get ready to wrap up this forced outage.
So now that everything has been boxed and shipped from site, we're bringing everything back together at the facility, the power plant. We're going to rebuild the unit. We're going to work on startup support and tuning support. The site has continued to move forward in their efforts of cleaning and replacing components, stator vanes in this case, as the failure was in the stator, S5 of this rotor, and then other capital spares being replaced as well. Checking for debris and alignment has taken place while the offsite activities were going on. And now that all of this has been finished up on site and all offsite activities have been concluded, everything will start to wrap up as though it were any other planned outage.
So the turbine's been buttoned up. A wrap-up meeting needs to occur between the service provider and the on-site staff. And then at this time, we're going to demobilize the crews.
So remember, moving forward from this, now that the turbine is back up and running, the importance of proper preventative maintenance, data tracking, parts pedigree tracking, and recommended inspections, and the proper evaluation of bore scope inspections. Preventative maintenance is key to being prepared and understanding data and trends in your unit, and allows for the ability to observe and make sense of developments and data. This is key to understanding not only what routine maintenance the unit needs per OEM documents, but the signs of the unit that it's giving during operational intervals, and that things may be veering in the wrong direction. Understanding what data is being broadcast into the control room from the unit is paramount, but just as imperative are the bore scopes of these units. This is our only look between maintenance intervals at what is really happening inside the unit. There are some great companies out there who can provide top-rate bore scope reports, OEMs and third-party vendors included, but power producers who are really staying ahead of the game are those who are taking the time to understand what that bore scope report has said and what it means for the unit and continued operation before filing it away for next year's outage. Where are the cracks in my unit and which ones should I be watching? What do some of the small rubs in my compressor mean, and what could they be signaling? What do I do with the data that's been provided? Am I watching for a crack for propagation, or should we be planning an outage at the next available interval to handle what it is we're seeing? Taking the time to understand what these reports are actually saying and going through it with a provider or a vendor who has experience in this industry and in the operation of these units and the repair of these units can be greatly helpful in your preventative maintenance practices. These are services that can be provided that go above and beyond the reports and discussions and that are important to keep the next finding from becoming a bump in the night. So with that, we thank everyone for being involved over the last hour and listening to us. We've had a couple of bumps here on our end, but with that, if there are any questions, we're happy to address them now.
Thanks, gentlemen. Yeah, we do see. I see a question here in the chat from Mr. Anderson. Does Sulzer follow the OEM recommendations for replacing hot gas path parts based on fired hours or number of previous repairs? Or will you recommend extending the replacement interval based on your shop testing procedures that might show how much usable life remains?
So definitely an excellent question that has been discussed for the last 40 years. So I would say the common stance needs to be always look at your OEM's recommended life, first off. Secondly, work with your service provider and get adequate inspections. Many life assessments can show that the base material is rejuvenatable and does have life left, or it'll tell you factually that the material is done. But it's just not sending in your parts for a typical inspection process. I mean, let's have a discussion as a business partner, and let's look a little bit further. Give us some run data, give us some parts history, give us some pedigree. If we see a set of buckets, let's say, while we're going through the inspection process, and it has 2 or 3 sets of serial numbers in that set, then we're gonna, let's take a look. When were these other buckets replaced within the set? So it's a great question, and it definitely needs to be asked, because we believe that the OEMs are conservative on their life assessments of the parts. And honestly, in our history, you can definitely run past OEM recommended intervals.
Yeah, and we make that business decision with a lot of our customers who, just like I'm sure everybody on here, as budgets get tighter over the years and more accountants are playing more and more roles within the operation systems of these units and how they're operated. Just because we've reached that conservative number that was provided by an OEM for a 7EA, in this case, it would be GER 3620 Rev P now, P as in Papa. But as we move forward with these customers and go through these inspections, and like we talked about in this presentation, having a Met Lab available to us at Sulzer is a huge help in assessing the remaining life of these components. So if you're willing to work with us, we're willing to work with you and take a look as well to make sure that there's still remaining life in these components.
All right, thank you. There were plenty of questions that were submitted via registration that I'd like to go over a little bit. And the first one is the big buzzword of today, supply chain. So what's your outlook right now, and what are you seeing with supply chain issues when dealing with in and out kits or consumables that might be needed in a situation like this?
Yeah, that's I think everybody on this call sees that personally and professionally, right? You can either get ahead of the curve or you can stay behind, but what Sulzer has done is increased our on-hand inventory. That, I'm not going to lie, there still are some snags in the roads for one-off purchases, but if the service provider is taking the time to evaluate the business and the current market, they should adjust their on-hand inventory counts. They should increase increase up to a certain point of their on-hand items, whether it's field service outage kits, whether it's spring clips for a combustion liner. I mean, if you truly think about it, $100 bolt for an aft bracket on a transition piece could push an outage out, right? If you're not properly managing your supply chain. So it's difficult right now, but you just have to stay ahead of the curve, ahead of the game.
All right, thanks. Mike, I'm assuming this one is going to be for you. Can you talk about what you're seeing in terms of fuel nozzle and combustion system damage of units that are coming through the shop?
So this year to date, we have seen, and I'll hit directly on 70As. Year to date, we've been made aware of 3 failures of transition pieces on the EA, and they were all dry low NOx operations. Those machines that had the transition piece failures have been cycling more. So we're definitely seeing new failure modes as compared to baseload operations. Fuel nozzles are definitely, they're getting worn out quicker. We're seeing, like in the transition pieces, we're seeing some new indications in areas that we haven't seen before. Yeah, it's the combustion system's taking a beating, y'all.
Yeah, and that not only stems from cyclic operations, but also running units at lower speeds and higher temperatures during those operations. We've seen a lot of units go into turn down because of availability or to try to push more value to stakeholders on site and in the marketplace and running at 50, 60, 70% load. And these units were not all designed to go down to those loads, and most of them still running legacy components are taking a beating from those higher temperatures that you see at those lower operating curves. So that in conjunction with the cyclical operation, more starts and longer runs, in a lot of cases, we're seeing people move out of the box of what they're typically expecting on these outages.
There's a follow-on from Ivan. Are you seeing these in both GE and PSM transitions?
So I'll be an advocate for PSM for everybody involved. They do make a more robust combustion system than the OEM. We've been repairing PSM components ever since I've been here, so 15 years, whether it's on the Siemens side or the 501F side or the GE side. So definitely build great combustion components.
There's a question here also about fogging and forced outages. Are you seeing an overwhelming correlation to units that have come in through the shop in a forced outage situation, that they're fogging quite a bit? Or
so we don't always receive that data from every customer, whether or not they're using inlet foggers or wet compression systems to try to boost performance of the unit. But anytime that you're increasing mass flow through those units beyond what the OEM was initially expecting you to see, whether it's from the OEM or from an aftermarket provider, the chance will run higher that you're putting more stress on the unit. You're getting a gain out of it by increasing mass flow and in turn increasing performance of the unit, but there is a curve that needs to be watched there for how much you're boosting the unit versus what the maintenance interval is going to be. And in the case of someone who is utilizing inlet fogging, we would recommend to make sure you keep up on your bore scope inspections and track data as much as you can on those units.
Thank you. We've got a question in the chat here from Nick Gobin. Does Sulzer ever work with insurers on behalf of the owner to support extensions on OEM hours for parts?
Historically, yes, sir, we have. We've done several different ways. We've done rainbow tests with customers and insurers. We've done lab analyses, but yes, we've done that. And then the question from David about the runout test area on the shaft protected coating. So I would assume it's this picture that he's describing, and this rotor is on a low speed balance machine, and the journal area of the compressor side, it's on a hard roller. So that's a shank balance machine. It's not protected. It's just roller on bearing journal.
All right. Well, if anybody has any more questions, please raise your hand, unmute yourself, or put it in the chat. Just looking back over the registration, it might be more food for thought than anything else. But if you have any input, that would be great. Scott Wright has a question on if power pools around the country are using start costs to properly value cycling. I guess when you take on this whole new risk profile, are the RTOs and the are they basically compensating owner operators for taking on this risk?
So we're not privy to a lot of those conversations, but colloquially we hear a lot of information from unit operators and plant personnel that no, typically that is not being accurately represented in their assessments when they're changing the operating profile of their units. And again, it's not really our business to help with that, but there are things that we can do to help at least address some of the concerns that changing operating intervals and operating procedures can have to the ensuing maintenance intervals for these units, and what someone could come to expect from a change in operating profile like that.
Just another challenge facing the industry.
As if we don't have enough, right?